Hey guys, so I know I've been slacking a little bit on acids and bases, but this video is just going to go through your acid-base study guide so that we can get a really good, clear picture of what we're dealing with. So first thing I want to look at is question number 1, and question number 1 says carbonate, or CO3 2-, readily dissolves in water to yield an alkaline solution. What is this substance classified as? Should be there between that last word and the question mark. And so the first thing we need to look at is this word alkaline. So when we look at that word, the word alkaline means basic. Okay, and so what they're saying is that carbonate is producing a basic solution. And so it wants to know, what is this substance classified as? So we could look at it as just being classified as a base, but we know that there are two types of base. Two types. You have a Bronsted-Lowry base and an Arrhenius base. And so what you need to decide is, okay, well, which one is it? Well, I'm going to kind of do part of number 2 at the same time because they really should have been worded or ordered differently. But a Bronsted-Lowry base is one that is going to accept H+ ions. Okay, and an Arrhenius base is one that will produce OH- ions. Okay, and so when we're looking at this, okay, now an Arrhenius base can also be a Bronsted-Lowry base, but not the other way around. So when we look, we notice that Arrhenius bases produce OH. And when you look at carbonate, CO3 2-, there's no OH. So our answer here is CO3 2- is a Bronsted-Lowry base because there is no OH- ions. And there's actually another reason. So if we look at carbonate, this 2- charge means that we know that negative things are attracted to positive things, so it will readily accept a hydrogen. And so that negative charge means that it will gladly accept the hydrogen plus ion that's part of the Bronsted-Lowry definition. So if we continue to do number 2, but look at what it means to be those acids, a Bronsted-Lowry acid is one that will donate H+ ions. And another way you could reword the donate and accept is you could say it loses H+ ions and bases are going to gain H+ ions. And then the definition of an Arrhenius acid is one that produces H+ ions. So the differences between the acid definitions are not very big. One thing that I would like to say is that with the Bronsted-Lowry versus Arrhenius thing, I know it can be confusing when you're thinking about how do you really tell the difference. So timeline-wise, Arrhenius, right, came first. And let's say he had the circle represents his definition, right? He had his definition of acids and bases, okay? And so substances like NaOH and HCl and H2CO3 and LiOH, all of these were included in it. And all of them, all the bases had the same characteristics, all the acids had the same characteristics. And there were some substances, though, ammonia is a perfect example of something that had all the characteristics of a base, but didn't meet Arrhenius's definition. And so Bronsted and Lowry, two different guys around the same time, both independently, so separately, came to the same conclusion that they needed to actually broaden Arrhenius's definition to include NH3. And so Bronsted-Lowry's definition just kind of tweaked things. Their acid definition did not change. They just kind of changed the wording from produces H plus to donates H plus. But it encompassed the NH3 and it became all about the hydrogens. And the way that you can really tell this is if you look at what happens. So if we take something like, for example, NaOH, that is an Arrhenius base. Okay, what happens is NaOH is ionic, so it's going to break apart into Na plus and OH minus in water. And so when it's in that water, the OH minus will react with the water and force the water, which is amphoteric, meaning it can do both, to donate a hydrogen. And so we have a base here, and what's going to happen is when it donates, it'll become HOH plus OH minus. So it's actually OH minus is on both sides of the equation. So not only does it meet the definition of accepting a hydrogen from the water, but it also produces OH minus. So the definition of an Arrhenius base is included in the Bronsted-Lowry definition, but it just widened it to include more compounds that they saw having the same characteristics. And so if we look at number 3, it says, what is the pH of acids? What is the pH of bases? And so when we're looking at this, we want to think about our time, or not our timeline, our scale. So if we're looking at the pH scale, it goes from 0 to 14, and in the middle we have 7. Now, if you are less than 7, you are an acid, and if you are greater than 7, you are a base. And if you're exactly 7, you're considered neutral. Now, an example of a neutral substance is water. And one thing to note is the more basic you are, the less acidic you are. So they're kind of inverse of each other's. So let's say I have something that has a pH of 2, and it's HCl. When HCl breaks down to form H plus and Cl minus, we know that this is our acid, right? Has a pH of 2. Now its base, Cl minus, that's its conjugate base, what it produces. If this is a very strong acid, that means Cl minus has to be a really weak base. So as you move this way, you become a stronger acid, which means you in turn have to become a weaker base. So you can think of a pH scale in terms of like opposites. As you move away from one thing, you move closer to the other. And so when we're looking at this same scale, if we look at number 4 says if a student dilutes 10 milliliters of NaOH to 100 milliliters using water, okay? That means we have a beaker, and let's say our acid, which is actually not true, is green. It's actually clear, but that would be difficult to draw, okay? It's green, and there is 10 milliliters of it right now. What happens is we add water to it, and when we add water to it, it goes up to 100 milliliters, okay? Now, in 10, like if you were to take 100 and divide it by 10, you would get 10, right? So we call this a factor of 10 because you have to multiply it by 10 to get to 100, or you have to divide by 10 in order to go from 100 to 10, right? So we're changing by a factor of 10. And because pH is a log, which remember, I showed you this formula in class, pH equals negative log of H plus, but you don't actually have to know it. What you do have to know is, trust me enough to know that I'm not going to lead you astray, but when you change by a factor of 10, your pH will go up or down by one whole number. Okay, now I could walk you through the math, but most of you probably don't even want to know the math. So if you do, you can come see me in class. But if we think about it, okay, we know that water is right here, right? It's 7 on the scale. And so if we're starting at something that has a pH of 12, right, and we're adding water to it, it could change by a factor of 10. It could either go to 11 or it could go to 13. So going to 13 would mean going further away from where water is at neutral, and going to 11 would be closer to water. And so one easy way to think about it is if I'm diluting it with water, then I'm going to go closer to water is, but because it's only by a factor of 10, I'm only going to move one pH number or scale closer. If I diluted it from 10 to 1,000, which is 2 factors of 10, then I would go from 12 to 11 to 10, right? So the more water you add, the closer and closer you move to neutral. So that's one thing to keep in mind there. The next thing we want to look at is number 5. So what is the strongest, assuming all are different bases? Okay, so keyword here is bases, because that means if I'm looking at a pH scale, that a high pH is an indicator of a strong base, right? And a low pH is an indicator of a weak base, okay? But one thing to keep in mind is that strength and its pH is dependent on concentration, which is what we see in this column here, right? We see our molarities. Now, our concentration is determined by how much it dissociates. Okay, so remember, acids and bases dissociate or they break apart. So for example, if we have a base like NaOH, it's a really, really strong base, and so it's going to break apart into Na plus and OH minus 100% of the time. Whereas another base, like ammonia, it can form NH4 plus by accepting a hydrogen, but it's not going to do that 100% of the time. It's going to stay NH3 a decent amount. And so one thing that we want to think about is we want to identify which one's the strongest. So they want to know which one is the strongest, and we'll go ahead and identify, we'll just kind of put them all in order. But if we look, we have 2 that are number 12, okay? Now, the number 12 is a high pH, so those are the ones we're going to look at as being our strongest bases, okay? So let's see if we can label them A, B, C, and D, right? Now, A has a pH of 12, but a molarity of 2. And C has a pH of 12 and a molarity of 4. So you might be thinking, well, hey, 12 has a high pH, concentration of 4, C has to be the strongest. And you would actually be wrong. And the reason why, and let's just go ahead and look at my amazing metaphors, is let's say you have a 5-year-old kid. And then let's say you have a 25-year-old person, adult, okay? But let's say they both can bench press 300 pounds, okay? So they both can lift the same amount of weight. Who's the strongest? Well, you might say, well, the 25-year-old, he can bench press 300 pounds, but so can the 5-year-old. And so one thing that you have to keep in mind is the 5-year-old is having to compensate for a lot of things. His arms are not as long, he doesn't have as much muscle mass, all of these things. So the 5-year-old is actually stronger for his size and for his weight than this 25-year-old is. Because if you think about the 5-year-old bench pressing 300 pounds at age 5, how strong will he be when he actually grows up to be 25? Kind of the same thing here is if we have a solution, right? So I'm going to actually just erase my kid metaphors here. Hopefully that helped you. Okay, is if we have two beakers, right? And let's say this one is weak or weaker, and this one is stronger, okay? This solution, let's say it's made up of A, and A is a orange molecule and a yellow molecule. Well, if it's really strong, that means that all of the molecules, 1, 2, will 100% dissociate. They're all broken apart, okay? But something that's weak, okay, let's say it's substance B, this purple and pink dots, okay, some of them will dissociate or break apart, but a lot of them are going to stay together. And so that's actually going to make it weaker, right? So if we know that pH is measuring how much H pluses there are or how many have broken apart, well, in this one, even if they both have the same pH, so let's say pH of 12, right? Well, yes, if we have a pH of 12, right? Then this one, this weaker one, will have to have a higher concentration, right? So it's going to have a lot more molecules in there in order to make up for the fact that not all of it is breaking apart. And so that means the strongest one is actually one with a lower concentration but the same pH. So that means A is the strongest, okay, and then C, and then the next strongest would be B because it has a pH of 9, and then D because it has a pH of 8. Okay, so hopefully that makes sense to you guys. Let's look at number 6. So 3 ways to monitor the progress of a neutralization reaction. Remember, a neutralization reaction is when you have an acid and you add it to a base. Okay, and what happens is it produces water and a salt. And salts are ionic compounds, so it really could produce anything. So for example, if we have NaOH plus HCl, we know that neutralization is a double replacement. So the hydrogen and the sodium swap places. And so we have HOH, otherwise known as water. And we have NaCl, which is our most iconic version of salt, called table salt. Now, if we wanted to observe this, right, we know that an acid is going to have a low pH, a base is going to have a high pH. When we add them together, they'll be closer to the middle. And so there are a few things in the lab that we could do. We could use pH paper or litmus paper, right? Kind of just like a paper strip that we could dip in there and see kind of the pH as we continue to go along. We could also use a digital pH meter, okay? And those digital pH meters act like thermometers. You just stick them in, tells you the pH. And then the third way is with a chemical indicator. And this is where you add a chemical to it that will change colors once it's reached certain pHs. And so the main one we've been talking about and using in class is phenolphthalein, which when it's clear, it behaves as an acid, and when it's like a dark pink, it's a base. And so when it's like barely pink, barely pink, that's when you reached a neutral substance, but it's very easy to go over. You kind of have to go back and forth, back and forth. And so we talked about in the last problem about neutralization, right? So when we have a strong acid, okay, so let's say maybe we have a HCl plus a strong base, okay, we know that it will produce water and salt, right? Now, if we have a strong acid and a strong base like NaOH, the final pH of our products will be neutral. It'll be 7. But if we look at question this, and actually this is if we start off with, like, let's say I have 100 milliliters of each. Okay, if you have a strong acid and a strong base, you have to have the same volume of both in order to reach a pH of 7. But if you look at number 8 says we have a strong base, okay, which is not a big deal, but we only have a weak acid. Now, if the goal of a neutralization reaction is to produce water and salt, and obviously neutralization, you're trying to get to a pH equal to 7, if you have a strong base, let's say we have 100 milliliters of it, you're going to need a lot more acid than 100 milliliters in order to compensate for the fact that the acid is weak. It's not producing as much ions because it doesn't dissociate enough. So we're going to need a lot more of this weak acid in order to compensate for it. And so when we're looking at number 9, what type of bonds do Arrhenius bases contain? Remember, all bases are going to have ionic bonds. And so in case you can't remember like what that looks like, okay, if we look at NaOH, for example, the correct way to draw that structure, remember ionic, we have a metal and a polyatomic ion, okay, and ionic compounds dissociate in water, so that means it'll produce Na plus, because the one valence electron from sodium is going to be transferred to oxygen, which will now have that full valence shell, and it has a negative charge. And so we can see here that that positive and negative shows ions, and so that we know that this is actually an Arrhenius base. But if we had something like a methyl group, which methyl is just CH3, and it was attached to a hydroxide group, okay, notice this line there, that indicates shared electrons. And shared electrons are an example of covalent bonding, okay? And so while there is that OH group there, this is not going to be behaving as a base unless we see that positive and negative ions, because this will not dissociate in water. So if we look at number 10, it says using the equation below, identify the class of each of the compounds. And so the important thing is to first figure out what is happening and what's changing. And so if we look at our products, right, on the right side, and we compare them to our reactants, we're going to notice that things seem to be switching around. We notice that the sodium kind of comes over here and is with the nitrate, and the hydrogen swaps places. And so by that, we know that this is a double replacement, or a wife swap, as we called it last semester, type reaction. And we know that when we have a double replacement with an acid, right, HNO3 starts with an H, and NaOH has that OH minus in it. So when we have a double replacement with an acid plus a base, that means this is a neutralization reaction. And so when it wants us to label everything, we know that HNO3 is our acid. NaOH is our base. Okay, HNO3 is donating this hydrogen. OH minus is accepting the hydrogen. It's just also happening to give the sodium away as well. So we have an acid and a base. HOH is none other than water. And NaO3, we have a metal and a polyatomic ion. This is just an ionic compound, otherwise known as a salt. And so for number 11, it says identify the parts of the Bronsted-Lowry equation. So one key thing about a Bronsted-Lowry equation is you're going to have two things. You're going to have, well, four things really. You're going to have an acid, you're going to have a base, you're going to have a conjugate acid, and you're going to have a conjugate base. Now remember, the word conjugate means partner. Okay, now these two things will always be products. And your acid and your base, these will always be the reactants. And we do this just to keep them from getting confused with each other. So when we look at HCl and H2O producing chlorine plus hydronium, or H3O+, we want to pay attention to how the hydrogen moves, because that is what the Bronsted-Lowry definitions are all about. So we see that from HCl, and I'm actually going to kind of highlight it for you. HCl, its partner on the other side is going to be Cl-, and that's because it is the one that most looks like it. And then water is going to be partnered with H3O+. And so we see that from HCl to Cl-, it has donated or lost a hydrogen, right? And so that means our acid is HCl. And by sheer process of elimination, if that is the acid, the only other thing on the left side of the arrow is H2O, so it has to be a base. But just to confirm, if we look at how H2O becomes H3O+, we notice that it gains a hydrogen, which is our definition. So our base must be H2O. Now, the partners, you have to look at it in reverse. If we look at how Cl- could become HCl, it would have to gain a hydrogen in order to do that. And so that means it's that chlorine, Cl-, is our conjugate base. Okay, so notice our acid is partners with our conjugate base. They're opposites of each other. Okay, and so that leaves H3O+ as our conjugate acid, which one thing you notice is that it starts with a hydrogen. It's got that positive exponent, so you know it's going to be wanting to give away that hydrogen to become H2O again. So remember, if you're starting with H, that's an indicator that it could be an acid, but don't get tripped up by water, which can be both, because remember, water as HOH, that first hydrogen allows it to act as an acid, and OH- allows it to act as a base. So you can see a little bit of both in there. And so if we look at number 12, when we're talking about strong acid versus weak acid, a strong acid is going to dissociate or break apart into ions 100%, or almost like 99%. But a weak acid is going to dissociate definitely less than 20%. Sometimes it's even less than 5 or less than 1. Now, the key thing with this is we measure it with a conductivity meter, because in order to complete the circuit and light up the light bulb that's on a conductivity meter, you have to have ions to transport the electricity, which is just free-flowing electrons. And so when we look at this, a strong acid will have a very bright light on the light bulb. of a conductivity meter, and a weak acid will be very dim because it doesn't have as many ions in which to conduct the electricity. Now, number 13 says we have 0.65 moles of an unknown acid that dissolves in water, and if 0.31 moles of hydronium ion forms, what was the percent dissociation of the unknown acid? So one thing to keep in mind is that hydronium is H3O+. So anything that's going to produce H3O+ when it's put into water has got to be an acid. That's a very acidic kind of compound. Now, if we start off with 0.65 moles of acid, right? And we know that 0.31 moles of our acid is now in this ion. That means you subtract the two, and that's how much is not ionized or did not dissociate. And so, easy way for a percent, remember, definition of a percent is the part you're looking for divided by your total or your whole times 100, right? So the part we're looking for is the part that dissociated, which would be that dissociation, you're talking about ions. And so we want the amount of ions, so 0.31 moles, divided by the total amount that's in there, 0.65 moles, times 100. And when you do this, you need a calculator. And you get, let's see, 0.31 divided by 0.65 times 100, you'll get 48%. So that's kind of in the middle. Not really a weak or a strong acid, just kind of chilling there for you. Flow chart for naming acids. Let's talk about this. So one thing we know is that acids, and before I get started, you might be wondering about bases, but bases are all the same normal naming system as we learned last semester. So if you need a refresher on that, I believe that was unit number 5. And so you can go back to that playlist and find the how to name those sorts of things. So with acids, you recognize them because they start with hydrogen. Okay. Now, if it doesn't start with hydrogen, it cannot be an acid because the definition of an acid is to donate a hydrogen. So if it doesn't have one, can't be an acid. So there are 2 types of acids in the world. There are binary acids and there are tertiary acids. Now, binary means only 2 elements. So that means you only have hydrogen and one other thing. So, for example, HCl. Whereas tertiary is 3 or more elements. And so an example of this would be H2CO3 or H2CO2. Now I'm putting 2 examples because we're going to use those 2 examples in it. So we have these binary substances. Let's start there. Now with binary, the first thing you're going to want to do is they're very simple. You're going to identify your element. So in this case, Cl, right? So we have chlorine. So you'll add hydro as a prefix. You'll change the ending to ic, and you'll add the word acid. So the way that plays out is Cl is chlorine. So you add the word hydro to the front. So hydrochloric, because we changed the ending to ic. And you add the word acid. So hydrochloric acid. Now, with tertiary compounds, they're not quite as easy because you have 2 types of polyatomic ions. You have ones where the ion ends in ATE, and you have ones where the ion ends in ITE. Now, The way you know that is by looking on the back of your periodic table where the common ion thing is. And so if you look on the back of your periodic table and find it, you'll see that CO3. Well, CO3 is carbonate. So H2CO3 is going to be in that category because it's carbonate. Whereas CO2 right there, well, that is carbonite. And so it belongs in this category. And so what you're going to do if it ends in 8, you'll change the ending to ic and then add the word acid. And if it ends in ite, you change the ending to ous and you add acid. And so the way that looks, carbonate, you change the 8 to ic, so it becomes carbonic acid. And carbonite, you change ite to ous, so it becomes carbonous acid, which sounds silly, and it is, so it's okay to laugh. And so you can use this flowchart to help you with number 15 to name the acids. So HClO3 is a tertiary compound because it has more than 2. And if you look, ClO3 is 8, chlorate, so that means it will be chloric acid. And ClO2 is chlorite, and so this will be chlorous acid. But HCl is binary, and so this will actually be hydrochloric acid. We look at number 16. Okay, it says what colors are strong acids on pH paper, litmus paper, in a solution with phenolphthalein, which that is spelled wrong. So phenolphthalein. Okay, in solution with bromothiol blue. Complete the above for strong bases. Easiest way to do this, guys, just create a chart. I love data tables. Maybe it's just me. But if we have acids, okay, and we have bases, let's put the indicators, right? So we have different indicators over here. We have pH paper. That's one that will turn many colors. Okay. We have litmus paper, and you have 2 types. You have red and blue, but we'll just talk about their colors because they're the same no matter which one. And then we have phenolphthalein, and then we have bromothiol blue. Okay, now there are actually a lot more other chemical indicators than phenolphthalein and bromothiol blue. There's methyl red, methyl orange, I think there's even a methyl yellow. The color indicates at least one of the colors that it will turn. Now in pH paper, acids, very, very strong acids, will be a really dark red. Okay. Whereas bases are going to be a extremely dark blue, almost black color. Okay. And then with litmus paper, acids will turn red. Litmus paper will stay red. Okay, so if litmus paper ever stays red or turns red, it's an acid. But if litmus paper turns blue, and it's actually like a red pink and like a pale blue for litmus paper, but if it stays blue or if it turns blue, then it's a base. And for phenolphthalein, we talked about this earlier, it's clear when it's with an acid, and it is pink, sometimes purple, depending on who made your phenolphthalein solution, if it's a base. And for bromothiol blue, you guessed it, blue is for bases, and the other color is actually yellow. So that's the end of your study guide. It's a 40-minute video, so I'm going to stop here. Hopefully you were able to review and that you should be good for your test on Thursday. Good luck.